All right, so last time we finished up with using our calculator to do those calculations. By the way, it's important. You do need to know how to use that one variable statistics function on your calculator, and we should use it a lot this year. So why do we use the same formula for sample mean and population means? Remember, we take the sum of our values and divide by n, or the sum of our values and divide by big N. But we use different formulas for the sample standard deviation and the population standard deviation. So I do want to try to explain this to you quickly and perhaps even maybe a little bit crudely, but I do want to, again, it's BAPS. It's beyond the scope of this course, so you don't need to know why, but it's not a bad thing to try to understand. So suppose we have a population of 1,000 kids, and we're going to take samples of size 10, and we're going to try to estimate the sample mean. We want to estimate mu. So we don't know what mu is. Suppose mu is 50. So we're going to take our sample, and it's probably not going to be 50. It might be 48. And if we take another sample, it might be 49 or 53. There's going to be variability from sample to sample. That's just the nature of sampling. But here's the thing. This is calculated by taking the sum of your x's and dividing by big N. This is our estimate based off of this formula. So the reason we use this formula is because if our true mean is 50, if we take a good simple random sample of 10 values and we calculate the x bar, we might be a little bit below, but if we do it again and 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 again, if we do it a whole bunch of times, actually, if we take every possible combination of 10 people from that collection of 1,000, then the mean of the sample means is going to be centered is going to be exactly the same as the population mean. So what that and you should say this kind of looks familiar. Yeah, what that tells us is that this is an unbiased estimator for this value. And that's what we want. So why do we use this formula to approximate that formula? Because on average, it's going to give me values that are centered right at that true value. Everything is good in the world. However, if, let's just say for example, that if we calculate the population standard deviation, and I'm actually going to use the word variance here because technically variance is the right word to use here. If I do the variance, which is x minus x, okay, this is going to be minus mu because we know the true value, squared, and we divide by big N. Remember the standard deviation, we'd have square roots around this. Well, we can talk about standard deviation, it's fine. Let's just say this value is, for example, 4.0. So what we're going to do is we're going to take samples of size 10, hopefully a good simple random sample, and we're going to calculate S, the sample standard deviation. The problem is if we use the same formula, if we use x minus x bar squared over n, then we might get something, or we will get something. But the problem is that when we take a look at those collections of sample statistics, these S's are going to look maybe something like this. I should have thought a little bit about whether I should put them above or below. We want to divide by a smaller number. These probably should be on the other side, but it doesn't matter. And if you notice, the average of these is not the same as the population value, because this is a biased estimator of this. Why? It's complicated, but it just isn't. Okay, so they had to fix it. Statisticians had to fix it, and they found that fixing it involved just doing this one little modification to this thing. You just divide by n minus 1 if you sample without replacement. And usually we sample without replacement. So now that means this one is an unbiased estimator of that one. Okay? So now what that'll do is that'll just shift this so that they're centered at the right spot. So why do we divide by n minus 1 when we do samples? Because that gives us a better estimate for the population standard deviation, which is what we want. Okay? All right. There we go. Done deal. In statistics, excuse me, a measure is considered resistant if extremely large or small values in the data set do not influence the measure. However, a measure is considered sensitive if extremely large or small values in this data set do influence the measure. Typo there. So for mean centers, we have mean, median, and mode. For spread, we have range, IQR, and standard deviation. So in class, I would ask, which ones do you think go here and why? And, you can do a little bit of thinking about it. Which measures of center and spread are resistant? Well, the median and actually the mode are going to be resistant. The mean is going to be sensitive. Why? Because the mean takes into account every value. Well, I guess let's take a look at our cheeseburger example. So right now the mean is 6, okay? And the median is also 6. So what happens if I take my last data point and turned it into 100? We got somebody that ate 100 cheeseburgers last month. Well, let's run the statistics on this thing again. It'd be good for us to review, right? Menu, statistics, stat calculations. Oh, come on, what's going on? Why this is lagging so much? And variable statistics. And let's put in our C-burger. Now this is going to, it looks like the same operation, but now I've got a different number in there. So if you look at the mean is now 21 cheeseburgers, but the median is still 6. Why? Because, right? No. This was our data set. When we count to the middle isn't influenced by an extreme value. But if you add them all up, this 100 does change the numerator in that formula, makes it bigger, so the mean is influenced. So how about spreads? Well, the range, hopefully you guys can see that the range is extremely sensitive. In fact, it only depends on the most extreme low value and the most extreme high value. So this thing is so sensitive to extreme values that we rarely even use it because it's just too sensitive. Between the IQR and standard deviation, which one's going to be sensitive? IQR is going to be resistant, standard deviation is going to be sensitive. Why? Well, for the exact same reason. Change in this value isn't going to change Q1 or Q3, but it does change the standard deviation, because the standard deviation, if you recall, takes into account the distance from the mean. Well, that value of 100 minus the new mean is 21, that's going to have a value of 79, and then you're going to square it. 79 squared, that thing is huge. So, and you can see this from our results as well. So if I go up to here, the original standard deviation was 2.45. But if I go down to the new one, the standard deviation is now 38.67. Whereas the IQR is still 8 minus 5, or 3. Okay? So this is a big pro for the median and the IQR. However, we love the mean and the standard deviation. So it has plenty of stuff going for it as well. This is kind of a rule of thumb. If you want to ethically report statistics, If a distribution is skewed and has outliers, then we should use the median or the IQR because those are not influenced by those skewed values or the outliers. However, if a distribution is symmetric with no outliers, then we use the mean and standard deviation because those are kind of the preferred measures. That's not saying that you can't report the mean and standard deviation of a skewed distribution. It's just saying that maybe the median is a better measure of center. Create your own title. I guess we could look at these values and try to come up with a data context, but whatever. Consider the distribution below. Mark where you think the measures of center are on the distribution. Okay, so mode is probably the easiest to find. You kind of fit a smooth curve to this thing. It's going to be the peak. So I'd say this is the mode. So how about the median? Where is the median going to be located relative to the mode? Well, the median is the middle. And I think it's pretty easy to see that there are more data points over here than there are over here. So the median is going to be further to the right. Now, I'm not sure exactly how much, so I'm just going to put it right there. I don't know where it's located, but I know it's to the right. Then what about the mean? Well, the mean is going to be influenced by these extreme values. I mean, this is a 26. This thing is going to pull that mean up more than the median. So the mean is maybe located right here. Okay? The median can be thought of as dividing your data set into 50% areas. The median, always cut your data set into 50% areas, right? And the mean could be thought of as the balancing point. If you guys have taken physics or just understand our world, I guess, a data point over here is going to have more turning power. It's going to turn that distribution more. So the mean is kind of like the weighted balancing point. Median cuts it in half. Mode is the peak, the local maximum. So if the mean is bigger than the median, such as the case is here, then the distribution is going to be skewed to the right. Similarly, if you have a distribution that is skewed to the left, your mean is going to be there and your median is going to be there. So if the mean is less than the median, then the distribution is skewed left. In fact, another BAPS topic, beyond AP Stats, we do actually have measures of skewness that are often calculated by taking some constant and looking at the difference between your mean and your median. Because the difference between the mean and the median are kind of a measure of how skewed the distribution is, okay? But we don't need to worry about that. If the mean is approximately equal to the median, then the distribution is approximately symmetric. Don't ever say things are symmetric. Say they're approximately symmetric, because rarely in stats is anything perfectly, anything for that matter. All right, so next we're going to talk about classifying outliers. Let's go to the next video.